Okay, Yang, is it okay if we get started?
Sure. Yeah, go ahead.
All right, you want to start recording? We are recording. Okay, perfect. All right, everyone. Welcome back to the second session of today. And we are very happy to have Jonathan Hauenstein from Notre Dame, who will tell us about applications of numerically solving polynomial systems. Please go ahead, John.
All right, thank you. So thanks to the organizers for putting this together, inviting me. Hopefully next time we'll be able to see everyone in person. So what I want to talk about today is three different applications. So one's in differential equations, one's in mechanical engineering, and then one is in machine learning, of how we're using numerical methods to solve polynomial systems in these applications. Okay, so just from a very basic mathematical perspective, algebraic geometry is the study of solutions to nonlinear polynomial equations. So we have some system of equations f of x equal to 0, and now we want to study those solutions. So you can get very complicated curves and surfaces and higher dimensional solution sets. What my research is focused on is on numerical side. So we want to develop and analyze numerical methods to actually compute those solutions. So to be able to use numerical techniques to find the solutions, to study the solutions, to describe their behavior. And so there are many applications that numerical algebraic geometry have been involved in. From the math side, there's lots of problems in real enumerative geometry that can be solved with numerical algebraic geometry. Mechanism design, which I'll give an example of today, solving differential equations. You can discretize to be able to get very nice but large systems of polynomial equations. And then you can also study chemical properties using numerical algebraic geometry. Because these slides are going to be posted, I thought I would have at least one slide of a general reference. So if you want more information, here are two books to look at later. Okay, so whenever you start talking about numerical methods to solve nonlinear equations, the first place you start is Newton's method. So you have this Newton iteration, which takes your previous value and then updates it according to this equation. So geometrically, you start at x0, you compute the tangent line, and you see where the tangent line intersects the axis. That's your new point. You find its tangent line where it intersects the axis. That's your next point, and you keep iterating. So when you keep doing this operation, what you hope is that you converge to a solution. And what's well known is that locally near a solution, you're going to have a region of quadratic convergence. Okay, as long as, of course, the slope of the tangent line isn't 0. So the tangent line will intersect the axis transversely. Then you get quadratic convergence in that neighborhood. So that corresponds to an invertible Jacobian matrix. So the whole idea of Newton's method is, how do we know we're in this quadratic convergence zone, which is beautiful from a numerical perspective. But if we're far away from that region, we get chaos. So here's an example of x to the 4th minus 1 over the complex numbers. So of course the roots are the 4 roots of unity. So you have 1, I, minus 1, minus I, and nearby they're all non-singular. So you have beautiful quadratic convergence spacing. So you start anywhere near here, you're going to get very quick convergence to that root. However, if you're far away, you don't know where the roots are, you can land into these chaotic boundary regions. And then small perturbations will lead you to completely different answers. They may not converge. They may take a long time to converge. numerical errors can accumulate, and then you're sort of lost. So the whole name of the game on Newton's method is how do you find good starting points so that you can converge quadratically to the nearby solutions. And the way that we do this in numerical algebraic geometry is we're going to use homotopy continuation. So the way you find good starting points is you pick a different system and you start with its solutions. So if you want to know what are the solutions to a system, well, construct a system with known solutions. So that's the whole idea of homotopy continuation. Change the problem into something easier that has known solutions, and then deform the family back to where you want to go. So in the picture here, the starting point is at t equal to 1, and you have the 3 roots of unity. So the 3 roots of unity, we started with a really nice system that we can easily solve. And then you construct this family parameterized by t, and these solution paths will converge to the roots that you want to find. So how does this help with Newton's method? Well, at the very end, we have a numerical approximation to the solution, so we can use Newton's method there. But along the path, you can use the properties of the path to be close to it so that you can then use Newton's method to correct back to it. So you start with a known point. This has a smooth path passing through it that you can approximate. And so that gives you a nearby point. You can use Newton's method to correct. Predict, correct, all the way along to the very end. So we're turning the ability of, or the inability to find good starting points for Newton's method into the ability to track solution paths from known start points that allow you to approximate this endpoint. Now you have a good starting point for Newton's method that you can quadratically converge to give the answer to arbitrary precision, however you would like. Okay, so that's the whole idea of homotopy continuation. We don't know where to start, so we're going to pick a different system with known solutions and start there, and then continuously deform back to what we want. So let's apply this to a system of parameterized ODEs. So we have this parameter lambda in this 2-point boundary value problem. So for different values of lambda, say 2.75, you have these 2 solutions. When lambda is a little bigger, those 2 solutions look like they're coming together. And the question is what value of lambda do these actually match? Okay, so from a theoretical perspective, you know that there is some parameter lambda naught where there's 2 solutions. If you're smaller than it, you have exactly 1 solution, so that means those 2 solutions merged. And then once you go beyond it, there's no solutions. So what we want to do from this ODE is approximate this critical point, this lambda naught, where these two solutions are actually merged together. And so what we want to do is we want to use a homotopy that forces these 2 solutions to come together. So we're going to use a homotopy to deform these 2 solutions so that they match. So this is just a simple idea. So rewrite your differential equations into a system. And now we just stack that system. Because we have 2 solutions, we stack it up twice. So we have the y solution, say the blue one, and then we have the green solution, the z. And so we just stack up the system twice because we have those 2 solutions. And then this last equation is the homotopy. This is actually the thing that's going to force the solutions together. So at t equal to 1, we have 2 distinct solutions. So we just start with 2 distinct solutions, And this equation is trivially satisfied because we start with y equal to y star and z equal to z star. So when t equal to 1, this is trivially satisfied. And now what the homotopy does is it forces t to 0, and so it forces y to be equal to z. So this homotopy is going to force these two solutions to come together. So this is this whole idea of we don't know where to start, or we don't know what the value of lambda naught is, but we're going to start somewhere that's easy to compute. Plug in 4.25. You can use shooting methods to be able to compute the y star and z star trivially, and so you have a place to start. And then you use homotopy to be able to go where you want to go, meaning y equal to z. Okay, so this animation is animating what the homotopy is doing. So each step, we're going a step in t, and we're forcing those two solutions closer and closer together. And then at t equal to 0, we just read off what was the critical value of lambda. So we just find the endpoint of this. And so using different discretizations, number of grid points, you can see that this critical value is converging to somewhere around 4.755, give or take a little bit. So now we can be able to approximate this critical value to arbitrary precision that you would like. Okay, so use shooting methods to be able to trivially get the start points, and then we can use this homotopy to force the solutions together. So now the rest of my talk, I want to talk about energy landscapes. So what we want to do is we want to look at critical points of an energy landscape and try to understand the behavior. So of course, potential energy landscapes show up often in, say, protein folding or chemistry or biology. Sometimes they're very complicated, and so you don't want to try to find all of the critical points. But if things have a nice structure, for example, suppose your function is a nice polynomial, then you can use the techniques from numerical algebraic geometry to find these minima, these critical points, as well as saddles and maxima as well. Okay, and so what we're going to do is we're going to look at finding best fit curves. So you have some data, so you're given some data, and all right, the first best fit curve is a best fit line. So, you want to find the best fit line to that data. So a line has a slope and an intercept. And so you have your line mx plus b, and you want that as close to yi as possible. And now if you take a sum of squares, this will give you a nice fitness landscape. It's nice polynomial, and so you can take its derivative, set it equal to 0, and we know from the linear case you get this unique critical point, which is the best fit line. So now instead of lines, we want to look at different objects, different curves that fit our data. And in particular, we want to look at curves which are drawn by mechanisms. So we have some mechanism. As I turn this angle here, this angle is going to be the response. And so I can look at, fitting a function to this response. And then we can also look at, in machine learning, again, you're trying to find parameters that best fit your data. And so we'll look at these two applications of this best fit idea using these energy landscapes. Okay, so the way that things typically work in mechanism design is you formulate a problem. So the mechanical engineer will formulate a problem. They'll plug it into their favorite optimization solver and try to compute lots of local minima. If they find a design they like, they build it and they're happy and they move on. If they don't find a design they like, well, then they tweak the problem a little bit, rerun the optimization, and try to find it and repeat the cycle. So it's a lot of iterating between optimization and formulation. And so that's where the art of mechanism design comes in, is the designer can take this output and try and tweak it so that you get something that has all the properties that they want. From a mathematical perspective, if you look at this fitness landscape that this optimization solver is going to have to navigate, what you often find is there's inferior minima, which have large basins of attraction. So if you start in those regions, the optimization solver is going to return that one very often. You can have higher dimensional degeneracies that can attract lots of solutions with the optimization solver. And oftentimes, the one that's sort of superior that you want to find has a really small basin of attraction. So you kind of have to get lucky to be able to find these superior minima. And so the obvious idea is, let's use homotopy continuation to be able to compute all of these critical points and analyze them. So if we have the whole library of them, then we can decide which ones are good, which ones are bad. We don't have to worry about basins of attraction because we're going to use these homotopy paths to converge to them. So let's apply this to a problem. So here's the linkage we want to design. We're going to have some curve that's input, and we're going to have this output be curves at 3 different angles. So what this is doing is turning a straight line curve that's, say, vertical into curves at different angles. So this is just recreating the same curve, just at different angles. So we want to use a sum of squares along these different design curves as our fitness, and then we want to minimize that. So if you plug into, say, Bertini to be able to compute these, you come up with 12 critical points. And then you can look at their fitness and you see, okay, this one, it has the minimum. It turns out to be a great design, and we actually built this out of metal and tested it. So this is what you really hope for. The global minimum is the best. It really has all the design characteristics you want. You can test it at different angles, and the error is actually really small. So this is a really nice design that we can actually do. But that's very special. That doesn't happen often, and so that's what I want to talk about next. Suppose we're trying to design a finger link. Okay, so we have a finger link here, and as this rotates, we want to rotate the other side. So we want to be able to recreate how a finger joint moves. So what my colleagues Ervin and Mark did is they took a picture of their finger moving, and they got this raw data points, and then they did a quadratic fit. And so what we want to do now is we want to design a linkage that can best fit along this curve. So we can design a finger link. And now here comes the difficulty, which happens often in practice, is this degeneracies. This has a degeneracy. If this link length is 0, then this angle and this angle are independent of each other. And so they can be anywhere they want to be. And in particular, they can fit this data as accurately as you want. And so if you just use a standard optimization solver, you're going to get this degenerate global minimum, and that's not very practical. And so here's sort of a cartoon of what happens. You have this global minimum down here, which of course is completely degenerate. It can satisfy the conditions, so your fitness is 0. If you just use an optimization solver, you're going to get, of course, the global minima, but you can also get some other local minima, but they're very inferior. And so what we want to do is we want to use homotopy continuation to explore the trajectories along here. So we have actual paths now between, say, saddle points and this global minimum that we can now track along and actually use those in our designs. We don't have to be just looking at local minima. We can look at whole paths in between them and construct mechanisms from there. And so this is really helpful for a designer because now they have more freedom to be able to make changes, search along trajectories. And then from a mathematical perspective, it's really hard to formulate their criteria. If you're going to do some mechanical engineering, you have to worry about torque and bending and how this all impacts the linkage. From a mathematical perspective, we're ignoring that. And then the other thing is you have branch defects. So you want to be able to go through these points in an order along a same curve. But you see here, this is the same mechanism, but it has two different branches. It kind of approximates some of them along one branch, and then it jumps to the other one. So mathematically, these are very, very hard to formulate. And so in our problem, the best one, the best non-degenerate, actually has branch defects. And so if you're just looking at minima, local minima, you're going to be so far off of where you want to go that we really can use these homotopy paths and study the linkages along them to get very good designs. So I have some time, so let me demonstrate this in our Mathematica interface. So we put together a Mathematica interface. It uses Bertini as its homotopy continuation on the back end. And then we use Mathematica to have a nice GUI to be able to demonstrate this. So you can track, so this slider allows you to track along this path. So let's go all the way to the end. Here you see this is the global minimum. Completely degenerate. It can satisfy the objective value to whatever precision you want, because this angle and this angle are uncoupled. If you go to the saddle point, now you see, this thing has some crazy defects happening. So you don't want to use the saddle point in the design. But if you look at the path between them, you can get really good mechanisms. They're not critical. They don't satisfy the critical point criterion, but they actually are very practical in terms of the design. And so you can get really small objective values that accurately track along your curve by looking at this homotopy between the critical points and the global minimum. So you can pick different branches, and now you can track along those branches with this slider here. Of course, it degenerates into this degenerate mechanism, but you have these other ones that you can do. So just by looking at these homotopies and these paths, you can actually find useful things for your problem. So this gives the designer a lot of freedom to be able to to find new mechanisms that wouldn't come out from, say, just using optimization. Great. So now let's move on to my last example is on regularization. So commonly, you're going to have noisy data. So when you look at this response data from moving your finger, you get sort of noisy data. It doesn't quite fit sort of this quadratic curve. And so what you do is you sort of regularize. You don't want to exactly go through the points, or because then you're going to overfit your data. You're going to model the noise. So you want to create something that sort of looks at the underlying properties without getting too crazy. And so the common technique is to regularize your data. So let's look at this in a mathematical perspective. You take your fitness function and you add some constant times your regularization function. So this lambda is your regularization parameter, and you have this regularization function. So classic is ticking off regularization, which is also called ridge regression. And so you just take the 2 norm of your points. So you want to find values which minimize the function, but also take into account its length. So you don't want things that are too long to be able to do this. So this is a classical problem in optimization, how to look at this regularization function and set up your problem. Okay, so our accepted work was we wanted to study what regularization does in deep linear networks. We picked deep linear networks because we could actually solve a lot of the problems there. Made it easy from a theoretical perspective to set up the polynomial equations, use homotopy continuation to compute the answers. So here's the fitness function. So you have your input data X, your output response Y, and then these W's tell you the linear network structure. So we want to best fit our data, but we also want to do this in response to this ticking off regularization. We don't want these values to get too big. We want to keep the entries of W small. And so, of course, the best fit line fits exactly into this structure here. So best fit lines can be solved in a deep linear network. So if there's no regularization, then you can actually write down an analytic expression of the critical points. And in fact, there's no bad minimum. So every local minimum is a global minimum. And in fact, you get lakes of these local minimum or lakes of global minimum because of over-parameterization. You can always throw in an invertible matrix somewhere that cancels off. So this is the idea of what happens in this fitness landscape. Is sort of everything just comes down and then you get this big lake of minima down here at the bottom. Everything is equivalent. And so any one of those points will work. The problem is because it's positive dimensional, it causes a lot of issue on the numerical side. You have ranked efficient Hessian. This slows down the optimization. And so regularization is used to make things nicer. Okay, so you want to use this perturbation to sort of smooth things out. So then you have this nice non-singular minima. The problem is that if you just take your classic ticking off regularization, you haven't destroyed all of the flat minima. They still can exist. Okay, so we give an example in the paper of just a very small example where you get this still a positive dimensional set of minima. Okay, so how do you get rid of this? Well, you have to just wait. You just have to weight your weight your points. So you throw in a weight matrix here and take entry-wise product. So you're weighting each entry, and now you've returned to the non-singular world. So everything is isolated, non-degenerate. Newton's method will converge quadratically nearby. You have all the nice properties you want from an optimization standpoint.
You have 5 minutes.
Yep, thank you. But regularization is a double-edged sword. So on one side, you avoid overfitting the data. That's nice. Okay, so when we throw in regularization, we don't have all of these crazy oscillations. We have a nice approximation. You don't have the ill conditioning coming from this flat region. So you have a nice point, meaning Newton's method is going to quadratically converge. Your optimization methods are going to be well conditioned there. But the problem is that when you throw in this regularization, you now get a very complicated landscape. So you have this very complicated landscape, which as it goes to 0, of course, trivializes to this nice simple region. So we can set up a homotopy now in terms of this lambda parameter. So things are complicated when lambda is positive, and they trivialize as lambda goes to 0. So you get sort of this trivial topology when lambda is 0, and you get a complicated topology when lambda is positive. The problem is when you're trying to do, say, training, you're trying to train your network, you can get stuck when you use regularization at these bad minima. So there's these non-global local minima that can and do appear when you use regularization. So you have to be careful about this. So you're trying to get rid of positive dimensional. So you're trying to make things nice so Newton's method converges, but at the same time, you're adding so much extra critical points that your optimization can get stuck. And so if you do this as a homotopy, now you can take a homotopy in terms of lambda. When lambda is big, you get lots of critical points, And then as lambda goes to 0, the critical points disappear because the topology trivializes. And so at the very end, you just have very few paths leading to this lake of minima. So what you want to do, what would be very nice, is sort of know how close you need to be so that you do deform off of the singular points, but you haven't added so much curvature that you get all of these critical points that destroy your optimization. Okay, great. So let me just wrap up. So the whole idea that I've tried to share with you today is that we want to use homotopy methods to be able to solve polynomial systems. We don't really know how to start Newton's method to give quadratic convergence. So you pick a different problem that's easier to solve, and then you deform back to your original problem. If you can compute all of the points, for example, the saddle points, the min, the max, this is very helpful in analysis and design, especially in these fitness landscapes. So you can provide sort of a utility for the saddle points. A lot of time I've been thinking, what are the saddle points good for? And so in particular, they're good at finding paths that lead down to the global minima. If the global minimum is degenerate, then these paths can yield really nice designs. And then we think of regularization as a homotopy as well, where we have this regularization parameter. We want enough regularization to avoid overfitting, but not too much to make this landscape very complicated. And so with that, thanks for listening.
All right, thank you very much. We have time for questions, and I see Sven has a hand raised. Please go ahead.
Yeah, hey, thanks a lot for the talk. So I have a question in the sense of how homotopy methods compare with other numerical approaches. So for instance, if I take the second example with where you're looking at the saddle points,
Yes.
This chemical essentially example, like this sounds like something I can typically throw a reinforcement learning kind of thing on in order to get things. So what are kind of, how do they weigh against each other and so on?
Yeah. So this is a great question. So when things are like this problem, this one you don't need any homotopy to be able to do. It's the global minimum. Optimization solvers can solve this trivially. In under a second, it's not hard to do. The difficulty comes from when you can't specify all the conditions that you want to do. So then it's more of, I can't write down the problem I want to solve. And so how do you have a method to solve a problem that you haven't told it what the problem is? Okay. And so that's where the difficulty comes in. So these other methods are very good when you can formulate all of the conditions that you want to solve, then they work great. The problem is how do I tell it to go through these points in order? How do I formulate, as this increases, I want to go from one point to the next. That's something that's difficult to formulate. And so the solvers don't know, the solvers will solve the system you give it, and it won't know these extra conditions. And so this is the challenge for other numerical approaches. So go ahead.
So in this example, how do I understand this in some sense? How can I not formulate it as with an overall, picking the solution? Like why can I not specify it as a reward?
Yeah, so you could say, all right, so I have this input angle and this output angle, and I want to say, okay, at this input angle here, I want the output angle to be greater than the output angle at the next one. And so you can put in all of these conditions like that. Yeah. But now your system becomes bigger and bigger in order to do that. Okay, so from the polynomial,
so in that sense, that two-dimensional thing, I don't see a problem with specifying a reward.
Right.
But if you say about this, actually leads to another question in the sense of scaling to higher dimensional examples, because
exactly.
That has been it's a crucial bottleneck, I guess.
Right.
Yeah. Oh, I know. So right. How do what?
Right. Exactly. I don't know how to formulate them in higher dimensions, and so the approach that we take is, well, let's write down the equations that we can easily formulate. Find these paths on the fitness landscape of them, and then investigate them to see if they're good or not. So what we're trying to do next on our, the last thing before we release our interface here, is we actually want to color code which ones are good and which ones are bad. So, let's say this region here has a defect. So then we want to color code based on that. So we want to turn these things that are hard to formulate into a posteriori verifications. So we don't know how to formulate them at the beginning, but we can check for them at the end. Does that make sense?
Yeah, I get the picture.
Yeah. And so, yes, if you can write down the system and formulate everything that you want, Optimization techniques are very good, but it's harder to do as the problems get bigger and bigger.
All right. Are there further questions for Jonathan?
I can ask another one.
Sure, go ahead.
So now this is all based on Newton's method in some sense. So now I'm always curious as a machine learning person, what about gradient-based method or gradient descent-based methods? Are they combinable with homotopy methods, or have people tried this? And
exactly. And so you can think of these paths between here as sort of gradient descent paths, from going from a saddle down to the minima. From a computational standpoint, that's great. From a theoretical standpoint, gradient descent paths aren't algebraic, and so you have to worry about error accumulation. When you're going down to a robust minima, you don't have to worry about that. But if you're going to a saddle point, then error accumulation can cause difficulty. And so what we do is we turn them sort of into algebraic paths that closely approximate gradient descent paths. And so that's sort of where you get these homotopy. That's the nice thing about homotopies, is you have an equation equal to 0. So you can correct the error. You can remove all the local error out of it. So if you're just doing
it depends. I mean, I'm sorry, but this depends on the loss function. So I can
that's right.
check it. So and start again, throw things away. I mean, there are ways to check it. So I think I have to see it on a problem by problem basis. And
yeah, exactly.
The really nice thing about gradient-based methods is the scalability of them.
Right.
Because you don't have to calculate the Hessian in that sense.
That's right. Exactly. But yeah, you can instead of using Newton's method, you can use other local correctors. Perfect. So thanks for your question, Sven.
And thanks, Jonathan, for your talk.